All right, guys, we are going to move right into our next objective, which is objective 5, which is going to focus on fission and fusion reactions involving nuclei. So we're going to first focus on fission reactions, and fission is the splitting of a really large nucleus. We're usually dealing with uranium and plutonium, and that larger nuclei is going to split into smaller nuclei. So we're taking a larger nuclei, it's going to go through fission to split them into two smaller ones. So I had students once that used to always say fission, division, that idea of splitting. And she was right. So if an isotope like uranium or plutonium is hit with a slow-moving neutron, it captures the neutron, it makes it incredibly unstable, and then it's going to break down or split into two smaller atoms and release a great deal amount of energy. And also more neutrons are always going to be produced. So in this little graphic, where it says figure 1, you have this uranium nucleus, uranium-235. You have this slow-moving neutron that's going to come in. It's going to combine with the uranium atom. It's then going to split into this barium-141, this krypton-92, release a huge amount of energy. And then these little guys are our 3, in this case, 1, 2, 3, are 3 neutrons that also get released as a result of this fission reaction. So those 3, in this case, neutrons, can then go on and collide with 3 other uranium-235 nuclei and cause those to fission, producing 3 more neutrons. So if you keep going with that, with like, okay, those 3, and actually I've kind of messed this part up here, where this would be 9 neutrons. So here's my 3. Those 3 atoms would all together release 9, and then this would be 27, and then 27 times the 3 that those 27 atoms would release would actually go up to 81 here. So you can see very quickly that the number of fission reactions can undergo what's referred to as a chain reaction and basically cause a huge amount of energy that can be released. And whether we can control that or not control that can make a big difference in how we use fission. So these are just some examples. These are ones that are already in your notes. You can see here kind of the general format of this is going to look very similar. In both of these, we have uranium-235. They get hit by a neutron, and then they're going to split into 2 smaller fragments. So in this case, we have barium and krypton, or we have xenon and strontium. So both smaller than the original uranium. And then in both cases, we have extra neutrons that are produced, 3 versus 2. Now, you will sometimes see, which is why I kind of added this in here, is you may have a fission reaction where you have to determine, say, how many neutrons there are, what's my missing fragment that we produce from our fission reaction. So use the same strategy that we did in objective 4, where we're going to balance out the left and right in terms of our top mass numbers and our bottom atomic numbers or charges. So if I go ahead to figure out, and this is looking for what X is, so how many neutrons does this fission reaction produce? So I'm just going to use the math that I've been using so far. So 235 plus my 1 up top has to equal 135 plus 97. And then what I'm going to do here is I'm going to put X times the 1. Okay, so I'm going to basically use that X to multiply my top number up there. So when I do this, I would get 235 plus 1, which would give me 236. And then I would have 135 plus 97, which would be 232 plus X. So in this case, X, if I do 236 minus 232, X is equal to 4. Okay, the bottom number I don't have to worry about because of that 0 there, so it makes it easy. I'm just going to focus on the top number. So what that would mean would be that this would actually release 4 neutrons from this fission reaction. So again, balancing out the mass numbers in order to figure out how many neutrons we get released. You're going to see something in the CK12 about that. So I wanted to show you an example that I could explain to you as well. And there's a video on there that goes over these even more. So you got to be able to identify, such as these guys, of what does a fission reaction look like so you can identify it. And then how do you figure out a missing particle using kind of our conservation of mass in that case. So like I said, a fission chain reaction can occur. If it's uncontrolled, then it's going to release huge amounts of energy than like a system can handle. So an example of this would be like a fission bomb or the atomic bomb, where they utilize the chain reaction of a fission reaction in order to release a huge amount of energy that would be destructive. Now, if we can control the chain reactions effectively, then we can actually get a continuous source of useful energy, which is essentially a nuclear reactor. So in a nuclear reactor, those fission reactions release energy. That energy then heats up water. I think I can zoom in here. Is going to heat up water. So, sorry, let me move this over. It's going to heat up water that's in like this little reactor core in here. Okay, which then, and in the reactor core is where you have your uranium that's undergoing the fission. That's over here, the nuclear fuel. Okay, that is undergoing fission. It releases a lot of energy. That energy is going to go into the water. The water absorbs it. And then as the water moves through the system, it heats up another source of water, okay, in here, which then goes to steam. So it goes from liquid to a gas, and that gas travels through, okay, it spins the turbine, okay, and then that creates the energy or electricity, and then it goes back through the system. You'll see in some of the videos too, the importance of the control rods. So the control rods can lift and lower and control basically the movement of the neutrons and how much fission reactions are occurring. And that way we can control the energy output that's occurring within the reactor. Okay, so you can kind of see some advantages and obviously disadvantages, but advantages is not giving off CO2 like some of our fossil fuels that we use to generate electricity. Ultimately, it has a high power output, so it produces a lot of energy for what we're using. It's considered a cost-effective fuel source, so there's only a small amount needed. There's no fossil fuels involved, so it's better for the environment in many ways. There's obviously some disadvantages. There is like considered to be thermal pollution to water sources. Initial high cost to actually build the plants and get these going. You do have hazardous nuclear reactor waste. So how do we deal with the reactive waste that's produced? And obviously there's always that potential for disaster if error were to occur that we can't control those fission reactions. Okay, but this is the basis of our nuclear reactors, and we'll be looking more into that with some different activities. The other big reaction besides fission is nuclear fusion. This is another reaction that releases a ton of energy. Fission and fusion are going to release more energy than any other process that we talk about all year. So in this case, it's the opposite. Here we have light nuclei, so small nuclei, hydrogen, helium, that are going to combine to produce a heavier nucleus. So in this case, if we look at these examples, we have hydrogen 2 plus hydrogen 2 making a larger helium atom. Okay, you're almost always going to see two hydrogens combine in terms of our examples from our Regents chemistry curriculum. You could see hydrogen, helium, or even a lithium involved. Here we have the same idea. Here we have hydrogen 2 plus hydrogen 3 to make a heavier, that should be an arrow, heavier nucleus. In this case, we just have an extra particle, a neutron, that's emitted. And again, a ton of energy that's released. So fusion is how all stars produce their energy, including our sun. So there's fusion reactions that are occurring on our sun, producing a ton of energy. Fusion reactions, though, require very high temperatures and pressures, which is why this can occur on our sun. Because you are forcing a positive nucleus and another positive nucleus to collide. And the reality is they want to repel. So it takes a lot of high temperatures, so fast speeds of the particles, and a lot of pressure to force those together and actually undergo the fusion in that combining process. Now, fusion can actually produce more energy than nuclear fission, which is why scientists in various fields are trying to figure out a way to use nuclear fusion in terms of a nuclear reactor, because there's fewer pollution problems. We're dealing with hydrogen, helium atoms. There's not that radioactive waste that's left over. But there is a challenge right now to develop materials that can withstand those high temperatures and pressures to overcome the repulsion. So hopefully in your lifetime, we'll see a nuclear fusion reactor and what they can do. So one big similarity between fission, which is splitting an atom, and fusion, which is combining atoms, is that both of those reactions, like I said, are going to produce massive amounts of energy. So why is that? First off, there's a binding energy that holds a nucleus together. So especially when you think about neutrons or neutrals, but you're having these protons that are all positive that are being held together. When a nuclear reaction or rearrangement occurs, energy becomes released as a result of that. So that leads us to what's called mass defect. Okay. Any other process that we talk about all year, conservation of mass applies. Whatever mass we start with has to be equal with the mass that we end with. So the mass of the products is equal to the mass of the reactants. Fission and fusion do not follow this. The total mass of our products ends up being less than the original mass of our reactant. So a tiny bit of mass will seem like it disappears. Where did it go? Well, we know it has to go into something. We know matter, mass doesn't just disappear. Fission and fusion take a certain amount of mass and convert it into that massive amount of energy that I was talking about fission and fusion reactions produce. This kind of goes along with, we don't get into it too much, Einstein's famous equation, E equals mc squared, E being energy and m representing the mass that's involved in this conversion. So what you guys have to know, though, is that fission and fusion, why we always talk about these two together, is that they both release a ton of energy, and it is because matter or mass gets converted into energy. So that releasing of energy. Okay, so those are the big concepts that you need to be able to do with fission and fusion, being able to define them, identify them, compare them, and also talk about this idea of mass defect.